This is section 1.3 on continuity. So here we have a graph from 0 to 4. And we have some points of continuity and we have some points of discontinuity. So in example 1, investigating continuity. Find the points at which the function f in figure 1.18 is continuous and the points at which f is discontinuous. So let's go continuous. Continuous on, and the bracket means we're going to include that point. We're going to go from 0 to 1. Don't include 1. Union with, let's go 1 to 2. So we're not going to include 2. There's a discontinuity there, a removable discontinuity. Then union with all the way from 2 to 4. So 2 we have a discontinuity, and then this function is continuous all the way to 4 and including 4. So the discontinuity is x equals 1, x equals 2. So 1 and 2 are the discontinuities. Definition: continuity at a point, interior point. A function y equals f of x is continuous at an interior point C of its domain if the limit is equal to the function value. At an endpoint, a function is continuous at a left endpoint or is continuous at a right endpoint of its domain if the limit as a approaches from the right is equal to the function value, or the limit as x approaches b from the left of f of x equals the function value, respectively. Find the points of continuity and discontinuity. Find the points of continuity and the points of discontinuity of the greatest integer function. And we see at every integer we have a discontinuity. So find the points. Continuity is all non-integers. And discontinuous at all integer values. So here we have some different types of discontinuities. Here, this function is continuous at x equals 0 because if we look at the limit as x approaches 0 of f of x is equal to 1. So as we approach 0, the function value goes to 1 on the left side, and as we approach 0, the function value approaches 1 on the right side. So the limit is 1, and at f of 0, we have a value of 1. Now those equal each other, so that means the function is continuous at 0. Here, the limit as x approaches 0 of f of x is still 1, even though when we get there, there's no function value. So we're approaching 1 from the left, and we're approaching 1 from the right, so it has a limit, but f of 0 does not exist. So those two are not the same, so we have a discontinuity at 0. We have what's called a removable discontinuity. Now, it's very subtle, but we do have a function value up here, so we can say the limit as x approaches 0 of f of x is equal to 1. We're still approaching 1 as x approaches 0. We're still going to 1, but f of 0 is equal to 2. So the function value is actually up here at 2. Now, those don't equal each other, so there's a discontinuity. That is also a removable discontinuity. Now here we have a jump discontinuity. We have f of 0 is equal to 1. We do have a function value right here, but the limit as x approaches 0 of f of x does not exist because the left limit is 0 and the right limit is 1. So there's no limit at 0. So this is a discontinuity. It's called a jump discontinuity. Here we don't have a function value. We say that, here's what we could say about this. The limit as x approaches 0 from the left of f of x is infinity. And the limit as x approaches 0 from the right of f of x is also infinity. But these are not necessarily the same. So the left and the right hand limit they're not necessarily different, but they're just going to infinity. So there's no limit. And as a matter of fact, there's no function value. So f of 0 does not exist either. So this is called an infinite discontinuity. This one is an infinite oscillating discontinuity, and we really don't talk much about this one. Removing a discontinuity, let f of x equal this function right here. Factor the denominator. So here's number one. So we factor the denominator, x minus 3, x plus 3, and it says, what is the domain of f? So the domain is negative infinity to negative 3, union with negative 3 to 3, union with 3 to infinity. So everything except negative 3 and 3, essentially. Investigate the graph of f around x equals 3 to see if f has a removable discontinuity at x equals 3. So investigate the graph. Well, let's use our calculator here. So x to the third minus 7x minus 6 minus 6. Let's move that back over a little bit. Divided by x squared minus 9. So how about zoom 6? That's the standard window. So there we have an infinite discontinuity at negative 3, and it looks like investigate the graph and see removable. Oh, at 3. So if we go second, and we're going to calculate a value, and want to calculate a value at 3, notice it's blank. So that means at 3, there's actually a hole in the graph there. Now our calculators really can't show a hole in the graph. So has a yes. So yes, we have a removable discontinuity there. How should f be defined at x equals 3 to remove the discontinuity? Use zoom in tables as necessary. So what if we calculated 2.999? Whoops, I missed the 2. 2.999. That's very close to 3. It looks like we're at 3.3323. And then if we did, how about we go 3.00001 right here. Then we have 3.333. It looks like 3 1/3. So how should f of 3 should be, 10/3 to remove the discontinuity. Excuse me. Show that x minus 3 is a factor of the numerator of f and remove all common factors. Now compute the limit as x approaches 3 of the reduced form of f. So here's what it's asking us to do. Let's, we got to show that x minus 3 is a factor of the numerator. We got to show that x minus 3 is actually in here. So let's do this. Let's go, let's do this synthetically. 3, we got 1, 0, negative 7, negative 6. So bring down the first, multiply, add, multiply, add, multiply, add. So it is a factor of the numerator. And what we have left is x squared plus 3x plus 2. Now that factors into, so let's see. The top would factor, where should I put this? The top factors into that x minus 3 that we looked at right there. And then it factors, this factors into x plus 2, x plus 1. And that's going to be over if we factor the denominator, x minus 3 and x plus 3. Now look, those cancel. Now what they're asking us, show that it's a factor. We did that. And remove all common factors. We did that, removed all common factors. Now compute the limit as x minus 3 of the reduced form. So if we do the limit as x minus 3 of this piece right here, I'm going to skip writing that. If we plug 3 into this, we get 3 plus 2, that's 5, times 3 plus 1 is 4, over 3 plus 3 is 6. So we get 20 over 6, but if we reduce that, it's 10/3. Look, 10/3. So that missing point right there is the point 3 10/3. Show that the extended function is continuous at x equals 3. Function g is a continuous extension of the original function f to include x equals 3. Well, if you have this for everything except 3, then you get everything except for this point that we want to fill in. Then if you fill in that point, you say when x equals 3, the function is 10/3. we fill in that what we call a removable point. We remove the discontinuity by filling it in. The reciprocal function y equals 1 over x is a continuous function because it is continuous at every point of its domain. However, it has a point of discontinuity x equals 0 because it is not defined there. So we have this 1 over x function, and it certainly has a discontinuity. It has a discontinuity at 0 because we have an infinite discontinuity there. But the question is it a continuous function? And the answer is not quite what you would expect. It is a continuous function because it's continuous on its entire domain. Now, where it is not defined, it has a discontinuity, but it is still a continuous function. The intermediate value theorem for continuous functions. Functions that are continuous at intervals have properties that make them particularly useful in mathematics and its applications. One of these is the intermediate value theorem. A function is said to have an intermediate value property if it never takes on two values without taking on all values in between. The intermediate value theorem for continuous functions. A function y equals f of x that is continuous on a closed interval takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y equals 0 equals f of c for some c in a, b. So what is all this saying? Let's say a was 2 and b was 10. And f of a, or the y, is 1 and f of b is 8. Well, from between 2 and 10, if this is a continuous function, then the function takes on all the values between 1 and 8. In other words, you could find a c where the y value is 3, or 4, or 5, or 6. Now, it only guarantees between 1 and 8. There could be values less than 1, and there could be values of greater than 8, but it doesn't guarantee that. It would only guarantee between 1 and 8. Example 5, is any real number exactly 1 less than its cube? Compute any such value accurate to 3 decimal places. Write the equation, then investigate the graph to decide if there is, and answer, and then find the answer. Okay, so is any number exactly 1 less than its cube? So here's what I would do with this. I would subtract that x over. So we have x to the third minus x minus 1. So let's plug it into our calculator. I'm going to clear this. X to the third minus x minus 1. Let's go zoom 6. And yeah, we have a place where this is equal to 0. So we're going to say yes, there is an answer. We're going to calculate that 0, so number 2. So here's to the left of the 0, here's to the right of the 0, and then it says, all right, it says guess, but it wants you to get close to the 0 we're looking for. Now, in calculus, we always round to 3 decimal places. So 1.32, we could do 324. Now, you don't have to write both of these, but we could also do 1.325. Either one. This is called truncating. We're truncating the decimal at 3 decimal places, or we're actually rounding. Since that's a 7, that becomes a 5. Now let's take a look at what the homework is going to ask us to do. In exercise 1 through 10, find the points of discontinuity of the function. Identify each type of discontinuity. So let's see if this factors. So we have x minus 3 and would it be x minus 1? So there are 2 points of discontinuity. Now, when you have a value that makes the denominator 0, that's an infinite discontinuity. So infinite discontinuity at x equals 3 and x equals 1. Now let's say, for example, let's change this a little bit. What if this was a plus 1 and these canceled? Now that's a hole in the graph. So this would be a removable discontinuity. There's nothing that we can't take the absolute value of, so there are none. There are no discontinuities here. We can take the third root of anything, so there are no discontinuities there, and that's probably good for now. Number 12, Does f of 1 exist? Does f of 1 exist? Yes, it does. F of 1 exists. Yes. Does the limit as x approaches 1 of f of x exist? Yes. And the answer happens to be 2. It's not 1. The graph is approaching 2. The graph is not approaching 1. So we're going to say yes. Does the limit equal the function value? No. Is f continuous at x equals 1? It is not. The limit is 2. The function value is 1. This is a removable discontinuity. Is f continuous? No. At what values of x is f continuous? So continuous on -1 to 0. -1 to 0, don't include 0. 0 to 1, it's continuous. There's a discontinuity at 1. And then 1 to 2, don't include 2. And 2 to 3, don't include 3. What new value should be assigned to f of 1 to make the new function continuous at x equals 1? So we'd have to fill in this removable discontinuity. So f of 1, we want that to be 2. Now if that happens, if we make f of 1 equal 2, we remove that discontinuity and it's continuous there. In exercise 19 to 24, find each point of discontinuity. Which of the discontinuities are removable, which are not removable, give reasons for your answer. All right, so if we plug 2 into this, if we plug 2 in here, 1, 2, we get 3 minus 2 is 1. So we'd have this point right here, and it's at the very least an open dot so far. F of 2 is 2. F of 2 is 2. And then for x greater than 2, we're at a value of 1. But this has a slope of -1, so it probably does something like this right here. This has a slope of 1/2, so it's a little flatter right here. But this is a removable discontinuity. Find each points of discontinuity. So A, x equals 2. B, which of the discontinuities are removable? X equals 2. Which are not removable? None. Give a reason for your answer. Give a reason for your answer. The limit as x approaches 2 of f of x is equal to 1, and f of 2 is equal to 2. That's a removable discontinuity. Find each point of discontinuity. A. All right, x equals 1 and x equals 2. B, which of the discontinuities are removable? Only x equals 2, because at 1, this is a jump discontinuity. Give a reason for your answer. Limit as x approaches 2 of f of x is 1, and f of 2 is equal to 2. In exercises 25 to 30, give a formula for the extended function that is continuous at the indicated point. Now this is the difference of two cubes. So f of x is equal to x minus 1, x squared minus x plus 1 over x minus 1, x plus 1. Now these cancel. That's a removable discontinuity. Give a formula for the extended function that's continuous at the indicated point. So f of x is equal to x squared minus x plus 1 over x plus 1 for x not equal to 1. And we want this to be, let's see, what would be left? If I put 1 in here, we have 1 minus 1, that's 0, plus 1 is 1 over 2. And make it 1/2 for x equals 1, which would fill in that hole in the graph. That's probably good for that one. In exercise 31 and 32, explain why the given function is continuous. Well, this is over here at 3, 1, 2, 3, there's a vertical asymptote, and then the function looks like this. Explain why. The function is continuous on its domain. Now it's not continuous on a function, on a value that is not in its domain, and that's okay. So this is still a continuous function. In exercises 41 to 44, sketch a possible graph for a function f that has the stated properties. F of 3 exists, but the limit does not. That's like a jump discontinuity. So you could have, let's over here at 3, you could have a solid dot here, open dot here. So f of 3 exists, it's up here at, let's say, 6, but it does not have a limit. 43, f of 4 exists. F of 4 exists, so 1, 2, 3, 4. So we have a point here. And the limit exists, but f is not continuous at x equals 4. That means I have to have an open dot here. So an open dot, so approaching this and approaching this, okay, so it's approaching the same y value, but yet it's not continuous. So I could either leave it like this with an open dot, or I could say, well, the function value is up here, so either way would have worked. Find a value for a so that the function is continuous. So if we plug -1, so this parabola is a continuous function, and this parabola is a continuous function, but we need them to meet at the same place in order for this to be continuous. So if they meet, the two branches meet at different values, let's say over here at -1 actually, they're meeting at different values, that's not a continuous function. Well, if the two sides are meeting at the same point, that's a continuous function. Let's plug -1 in here. 4 minus, let's see, -1 squared is 1, that's 3. I need this to be 3 when we plug -1 in. I need this to be 3 is equal to a times -1 squared minus 1. So 3 equals a minus 1. I need a to be 4. As long as it's 4, that's a continuous function. Review, limit as x approaches 0 of this right here. Well, limit as x approaches 0 of sine of x over x plus, so let's go limit as x approaches 0 of 2x over x. Well, this is automatic 1 plus. Now those cancel. This is 2, so we got 3. Find a left end behavior model for and a right end behavior model for y equals 3x plus 2x. So who's dominating? If I plug infinity into here and infinity into this x, this is going to dominate. So that's a right end behavior model would be y equals 2 to the x. Well, now if we plug in negative infinity, so y equals 3 times negative infinity plus 2 to the negative infinity, this is really negative 3 times infinity plus 1 over 2 to infinity, and this piece is headed towards 0. So this dominates on the left hand side. So left end behavior model is just y equals 3x. Give any vertical asymptotes and the behavior on each side. Well, this factors into x plus 2 and x plus 1, and this is x minus 1. So there's going to be a vertical asymptote at x equals 1. Now, if those would have canceled, let's say both of those were x plus 1, well, that would be a hole in the graph. So vertical asymptote. Give it behavior on each side. So the limit as x approaches 1 from the left of f of x is equal to, so how about on the left? Let's go x squared plus 3x plus 2 divided by x minus 1. So let's graph it. 1 on the left. What did I do wrong here? Oh, I didn't do the divide. I never did divide. Insert, divide, graph. So 1 on the left is going down to negative infinity. Limit as x approaches 1 on the right of f of x is going, it's way up to the top there, it's going to positive infinity. Review for limits DCA. Give the location of each discontinuity and each type of discontinuity. Justify each answer. At x equals 3, we have limit. Oh, first of all, this is removable. Limit as x approaches -3. Oh, it's a -3, not 3. -3. We're looking at this right here. Of f of x is equal to around 4, let's say, but f of -3 does not exist. How about x equals -1? This is also removable. The limit as x approaches -1 of f of x is equal to 7, and f of -1 is equal to 4. So those are not the same. That's a removable discontinuity. X equals 2. This is infinite. Infinite. So the limit as x approaches 2 from the left is -infinity, and the limit as x approaches 2 from the right is positive infinity. And then finally we have x equals 5. This is a jump discontinuity. So right here, 5, jump discontinuity. The limit as x approaches 5, we'll just say that does not exist, and f of 5 is equal to 1.